We are continuing our discussion of reinforced learning, and we are using our frozen lake example where we have a starting state, we have a goal, and we're looking here at this 4x4 matrix where we have holes in the lake that we don't want to fall into, but we're looking at, can we successfully find a route to get to that goal. In our previous videos, we looked at the brute force method, which gave us 0 successes out of 100. In our Q learning, we were about 50% success rate. And so let's take a look at SARSA in this particular video. So we are doing a comparison between Q learning and SARSA, state action, reward, state action. Q learning is an off-policy learning method. It estimates that future Q as the maximum possible reward at any given state. So it is the ideal scenario, which considers, if we just go into a little bit more detail here, it looks at the rewards for the current action and then attempts to understand the rewards for possible actions after the current action. And so when it's considering those future rewards, it looks at the optimal, the ideal, the maximum reward possible from all the future routes that would come from the choice that you're making now. And in comparison, SARSA, which is an on-policy learning method, it estimates future Q, but it doesn't look at that ideal. It looks at policy and follows what is the algorithm recommends, what's most likely based on its current learning as opposed to the ideal future rewards. So let's take a look at what that means. And so I'm not a robot. We are here in our Reinforced Learning Python workbook, and you can access that at drstephpowers.github.io/BIA. And we are working here in Reinforced Learning as part of prescriptive analytics, trying to determine what the organization should do. What are the steps to the process that will get us to that optimal outcome? So let's go in here. Just a reminder, if you haven't worked through the rest of the workbook, that you need to install a gymnasium. So import gymnasium as gym. We're going to import tRange to track our progress. And we need to initiate the environment. So we're going to use gym.make and the frozen lake to create this 4x4 grid where we have our starting position on the top left and our goal on the bottom right. And then you can see the H's represent the holes in the lake and the F are the frozen. So we reset the environment and we use this print environment render to have it show. If you want this to show in Google Colab, you need to make sure it says render_mode equals ANSI, and then it says print in front of the environment render. If you don't have those two pieces, then in Google Colab, you don't get this image that you would say if you're using like Visual Studio Code. All right, so we need to know the number of states and the number of actions. And we can get that from the environment. The observation space tells us that there are 16 different states. That's because it's a 4x4 grid. That makes 16 spots. And then we have the action space that we can pull from the environment. And that is that we can go up or down or left or right. So we have our environment defined. And we'll just skip down to SARSA here. When we did our Q learning in our last video, we were able to have 49% complete the challenge and get to the goal. We could, of course, play with the hyperparameters to see if we can increase that and improve it. And so I'll just show you here. Here's our hyperparameters from our Q learning. We are also going to have hyperparameters for SARSA. The difference between the Q learning and SARSA is the formula right here about how we are updating or how we're doing Q learning. So we're updating this Q table. And just look here at the Q1 and then we'll switch to the SARSA. So you can see with Q learning, we have our current state here and the reward associated with it. And then what we have is that we have our reward from future states. And we are going to look at how much are we going to consider that new information. So that's our learning rate or our alpha for how much we're going to consider those future possibilities. And then what we have is that because Q learning is based on the ideal reward from those future states that would result So we make a decision, and then that means that there's now additional outcomes that are probabilities. And so what would be the optimal reward from those options that are left to us? So this here, this max, is that ideal. And then it gets adjusted. How much of that ideal are we keeping? That's this discounting rate or gamma that you see here, added to that reward. So I want to then show you for SARSA how it looks different. So I'm going to scroll down to the SARSA section. We'll come back to this stuff. But what we'll notice is that we'll notice really the only difference here in terms of this code is our Q table, our Q learning formula. So again, we're going to consider the current state and the reward that comes with it. We will have a learning rate. Okay, so how much are we going to accept this new information? Just like before, so that's that same alpha. Notice the difference here is we don't have that maximum in our scenario. So it's not the ideal then, it is then based on policy, what we expect to see based on the algorithm and what we've learned so far. So you'll notice that this line of code is different between SARSA and Q learning. So let's just go a little bit up here. So how do we do this? We start with an empty table for Q table that is going to be 4 by 16 because we have our 4 by 4 lake. So the number of actions up, down, left, right are the columns here, and the number of states, that is the 16 different locations on the lake. Then we have our hyperparameters. These are the same hyperparameters we saw for the Q learning. We're going to go through 20,000 simulations. We're doing a learning rate of 0.7, so we are heavily weighting that future knowledge. And we're going to assume they can't go more than 99 steps. So as they walk around the lake, they can go back and forth and back and forth and back and forth, and the game ends when they've walked 99 steps or fallen in the ice or made it to the goal. So we've set that maximum there. And then we have our gamma, that discounting rate for how much we are going to reduce those future rewards. So we have the learning rate and gamma that are both reducing down the future rewards. One learning rate is how much we're going to accept of the future, and then one gamma is how much of the reward is going to be taken into consideration. So then we have here epsilon. Epsilon is the exploration rate. And in both the Q learning and in SARSA, we have the same treatment of epsilon. That is, we are assuming that right at the very beginning, we're willing to explore all directions, but then the more and more we learn, the less that we are exploring. So there's exponential decay for that probability of which states we go to next. So when we look at this, we start with an empty list here for our rewards. We use T range to track the number of simulations we're going through. We're going to iterate through 20,000 times, each time resetting the environment. So we start with at start on the top left. So we'll start there at 0. And then what we are going to do is we will move through the steps. We're going to stop when done changes from false to true. So we'll start with it at false. And then we are going to go through up to those 99 steps where first we are randomly generating a number, comparing that to epsilon. That determines the action that we're going to take. Are we moving up, down, left, right? And then that puts us in a new state that has a reward. Perhaps that new state is a whole, in which case done equals true. And what we do after that is we update our Q table. So then our Q learning formula here, different from the Q learning one previously. This one's for SARSA. And we update the rewards. We set the state based on our new state. And then just like before, we're going to have it output if we are done, because either we fell into a hole or we met the goal. We're going to have it tell it to us and then tell us how many steps it made it before it fell into a hole or before it won. And then we have here adjusting epsilon, that exploration probability as we go through, and appending the rewards. So we're going to look at our score over time as we go through those 20,000 iterations, how many are able to actually make it through. So let's run that. Hopefully I did run the other ones. I can't remember if I hit them or not. Oh, I didn't, but that might be a problem. I didn't reset the table. So let me stop this. Stop. Okay, stop that so I can rerun it from the beginning. Okay, first we create an empty table. There we go. Then we set our hyperparameters. Then we run it. So it's not then populating something that we already populated. Okay, so let's go down. And so then we can start tracking. So we see there's one who's made it so far. And scroll down a bit further here. Too far. All right, this one didn't do as well. Only 5% of it made it through. And we could reset the environment, run it again, and see if it changes. We see here this one didn't perform as well as the Q learning. Q learning is an important terminology to know, especially in terms of the world of ChatGPT and generative AI, because when we look at ChatGPT, it is a combination of supervised learning and of reinforced learning. So we scraped the internet, gathered a bunch of data, analyzed all the text, and used that to train the model in terms of what sentences look like and how to talk about certain themes and topics. And then we use reinforced learning in order to improve that so that the ChatGPT can respond, create ideas, create menus, create workout routines for you, right? Can create these new entities from what it's learned from basically analyzing a bunch of text. And the ChatGPT and the generative AI, they're all using Q learning models for that reinforced learning aspect of this rather than SARSA.